Hello friends. Welcome to my YouTube channel. Now, in this session, we will study the power diodes. So here we have the power diode structure, and here we have the signal diode structure. So as you observe here, the difference between the analog electronics and the power electronics is the depletion layer, it also known as drift region here. So we are intentionally keeping a drift region here. So this is the reason, because in order to increase the power handling capability of power diode, how it happens. So as we know that from the basics of electronics engineering, we can say that, so here we have junctions. Let's say I will write the junction J1 and J2 here. So here I have only one junction J. From the basics of analog electronics or EDC, we can say that any junction, say any junction which is having highly doped layers on both sides. Suppose highly doped layers on both sides of the junction means it requires lesser breakdown voltage. So any junction which is having highly doped layers on either side requires lesser breakdown voltage, and any junction which is having any one side, so one side with lightly doped layer, lightly doped layer requires higher breakdown voltages. So here we are going to using this principle, we are going to intentionally add an lightly doped layer in between highly doped layers to increase the voltage blocking capacity of the diode or device. Okay, so plus means here we have highly doped layer, and minus means it's a lightly doped layer. So lightly doped layer increases the voltage blocking capacity increases. So here we can observe, here we have the characteristics of SCRs, sorry, power diode and a signal diode. In signal diode we have having the linear relationship between the current and voltage across the diode like this. So this is why we can model this diode as a piecewise linear model diode. So as we know that the engineers have the capability to design a non-linear system into a linear system, but as in case of power diode, you can see the current flowing through the diode and voltage across the diode. As you observe here, the voltage current carrying capability is in kiloamps, and the voltage blocking capability in kilovolts here in case of diodes, power diodes. So in case of signal diodes, it will be milliamps and volts like this. The maximum thickness of depletion layer or n minus layer decides the reverse blocking capability of the diode. So signal diodes will block a small voltage and power diodes will block a higher blocking voltages. To understand the power diode and signal diode, so now let me assume an analogy here. So this is not the practically, but it's only meant for to understand. So let's assume, so here we are having a charge. Okay, the charge has to travel from here to here. So the in order to travel the charge, there should be a path in between the source to destination. So let's say we will give the path like this. It is only to understand the concept of drift region. Second, for the same charge, I will give another path which is like this. So this is the another path here. So now observe here, in the first case it resembles the signal diode, and second case it resembles the power diode. So see here is signal diode here. In this case, when the charge is moving to trying to move from here to here, what is the length offered to it? It's less compared to this one. So resistance is proportional to length, which is less in this case here. But here the resistance offered for the charge to move from the source to destination is increases here. So resistance, well, because it's a length increases, so resistance increases. So by insertion of n minus layer, we are going to increase the resistance of the device. Resistance increase. Second thing, when In this case, the charge here moves from here to here and accumulates here. So here charge accumulation takes place here. That means charge storage takes place here. So once the charge storage takes place here, so I is proportional to Q. So as the charge more is more stored, the current carrying capability also increases in case of this type of structure here. So as the current increases because of charge increases. Now, so this is about on state. That means when the device is in on state. So now let me take off state. So in off state, so that means if you want to block the uh, that means if you're not allowing the charge from here to here, what is the length offered to it? It is less, so that the electrons may jump here and it will move. But here, if you want to block this voltage, the electrons is having very high length compared to this one. So the blocking voltage increases. So blocking voltage capability increases here. So by using the power semiconductor devices, that means which will have a drift region, that is n minus region, we can increase the resistance and we can increase the current carrying capability as well as voltage blocking capability of the device. So this is just analogy. If you understand it, okay, fine. If you don't understand, please ignore it. Now we'll go for the significance of drift region here. So here in the significance of drift region, if the anode is made negative with respect to cathode, that means like this, then the depletion region or N minus region across the junction enters into the depletion layer, penetrates more and more deeper. So that means if you are giving reverse bias condition here, so this region will increase like this. So it is increased like this. If you are giving reverse bias condition, that means you are going to increase the length of the device here when you are giving reverse bias condition here. So length increase. So length increase means these are immobile charges. Immobile charges which will not constitute any current. Okay, so that the resistance is increases, it will have more and more voltage blocking ability. So this increases the thickness of the depletion layer, reverse blocking capability of the diode increases. So higher the depletion layer or higher the thickness of the N minus layer, the higher the reverse blocking voltage of the diode. Now we'll see the reverse recovery characteristics of diode. So this is a very important one. So it explains the switching behavior of power diode. So here when the diode is conducting forward direction, some excess charge carriers are stored in the device. So when it is conducting, some excess charge carriers are stored here. So they are stored here like this. These excess charge carriers are mainly due to minority carriers. So these are minority carriers. Okay. Now when the diode is in switching on from on state to off state, the charge carriers are still present in the diode even after the anode current is becomes zero. So even you remove the current here, make the current zero, some charge carriers are stored here. So in order to remove these charge carriers and regain the equilibrium state or the previous state, original state, that means in that state no charge is present in this pit or valley here. So we want to get that state to say that the switch is completely off state. So what we have to do here is, so we have to remove the charge carriers which are excessively stored here. So hence when we are removing the charge carriers from here to the side, the movement of charge creates anything but current. Okay, so this process is known as reverse recovery process. That means whatever the charge carriers are stored in the region, drift region, so it has to be removed. This process is known as reverse recovery process, and the transition time during this process is known as reverse recovery time. So it has to be completely removed from this uh, drift region here. Okay, so observe here. So this is the IA increases from positive value, so it slowly decreases to here zero value. But when you are removing the charge carriers, so charges are moving, nothing but current here. So this constitute a current. So earlier the electrons or charges are moving in this direction, so that current is positive. Now when the current stops here, the excess charge carriers has to be removed. That means the current is moving in the reverse direction, so that the current is in negative slope here. So here we have seen the characteristics of reverse recovery characteristics of diode. So here practically we assume that 25% of IRM, so maximum value of reverse recovery maximum current. So when it reaches 25% of its maximum value, then we can say that the power diode is in off state here. So here we are assuming that, so this is the area of a triangle here like this. So it's like a triangle structure. So by considering this as a triangle here, so we will have some derivation here. So area of the above triangle is, so area is nothing but half into B into H. So based on that area, so we have derived this equation, half the base is TRR and H is IRM. So and if the slope of the curve is di by dt, so as you observe here, if the slope of the curve be di by dt, so the slope that we have seen here is, this is the slope, and we are assuming this interval divided into two parts, that is t1 here and t2 here. I will show you in the next slide. Here, so let's say the total required time is divided into two parts, that is a t1 and a t2, and the slope of the line is di by dt. So slope is nothing but m is equal to y by x. So in y axis we have current and x axis we have time period, say t1 here. So let's define a factor called softness factor. Softness factor S here. So which will decide the speed of the diode. So S is equal to T2 by T1. So from this, so TR is equal to T1 plus T2. So we can write this, substituting this equation here, we'll get this one. So T1 is equal to TRR by 1 plus S here. So from this, QR is equal to half into TRR into IRM. So half into, so instead of writing TRR, we can write as it is. And instead of writing IRM, we can write di by dt into T1. So T1 is nothing but a TRR by 1 plus S here. If we substitute this equation, then a TRR square is equal to, so 2 into QR by di by dt. So this is the equation that we got. So here we have the T1 and T2 time periods, and the softness factor is nothing but T2 by T1 here. For the high speed diodes, the softness factor is almost less than 0. That means ideally speaking, it is SF is 0 softness factor. For high speed diodes, softness factor is more. Okay, so we have to limit the high voltage spike by using the snubber circuit. Why we are getting a high voltage here? So I is nothing but C into dV by dt here. Okay, so if you want to make this I0, so voltage has to be a constant value, but during here the current is changing like this. In the case of that diode, it is varying like this. So during this period, when the suddenly the current changes, so because of that there is a voltage induced here. So this is because of due to stray inductance present in the system. That means suppose if you apply the diode as a rectifier, there we have RL load or R load like this. So because of this stray inductance, which will not allow sudden change in current. So when the current becomes 0 means it will dissipate the energy in the form of magnetic field, so voltage. So here due to stray inductance, so inductance property, because of that a high voltage spike will occur. So we have to limit the high voltage spike by using snubber circuit here like this. So here we have inductance, that is stray inductance. It is also known as source inductance, you can say. Next one, so classification of diodes we will see. So in classification of diodes, based on the reverse recovery time TRR. So based on TRR only we can decide whether it's a diode is a fast diode or general diode or Schottky diode. So the TRR is 25 milliseconds, means it's a general purpose or slow diodes which are used in laboratory, that is IN4007 as an example. So the current carrying capability is maximum 1 amp to several thousands of amps. So this is a current carrying capability. The voltage rating is 50 volts to 5 kilovolts, and this is normal PN junction diode. Next, fast recovery diodes means in fast recovery diodes we will use a gold. So gold means we can ask a question, sir, gold gram is some high cost, no? So with 1 gram of gold we can make some millions of diodes. So the gold makes, that means it will make the immobile charge carriers are more, so that it will fast recovers. Okay, so voltage rating is from 50 volts to 3 kilovolts. It diodes and the layers are doped with gold or platinum. This doping reduces the lifetime of the charge carrier in the depletion or drift region. So increases its recombination speed. So this is the reason why we use a gold here. So this reduces TRR time. As the time is decreases, so TRR time is less means frequency automatically increases. Switching frequency is more here. And Schottky diodes. So this is a majority carrier device. So majority carriers. So majority carrier device. So it's so fast. Okay. So fast means is what the current and voltage handling capability decreases. As I told in my previous lecture, if you want to increase the power handling capability, you have to compromise with frequency. If you want to increase the frequency, you have to compromise with power here. So this thing you can observe here. The rise time, the time is in nanoseconds. Switching frequency is more here. The voltage rating is only 100 volts. Okay, and this has the metal to short circuit the junction diodes here. Aluminum or silicon. We'll use N type here. So in this diode, the conduction only due to majority carriers, as we discussed earlier. So due to the absence of the minority um, carriers, the TRR is very high and reduced. Therefore, its operation is with the very high switching frequencies here. So they are operating at very high switching frequencies. Next, in general purpose diodes, the slow diodes are used here. Okay, in line or frequency rectifiers. So therefore, they are also known as a rectifier diode. So rectifier diodes means it's a slow diodes. Applications are used in rectifiers here. And in applications, let's say fast recovery diodes are used in inverters and choppers. Why? Because here there we are going to use forced commutation. So we force a turn on the turn off of the switches. So we require fast switching operations here. And these Schottky diodes, in these diodes, the reverse blocking capability is limited to 100 volts because of thickness of depletion layer. So it's very small. So these are used in switched mode power supplies. So important notes here is the TRR, the reverse recovery time, decides the maximum switching speed of the device. The diode is an uncontrolled switch because there is no control terminal to control the on and off its states. Okay. So thank you friends. If you like my videos, please subscribe and share with your friends and like. Thank you. Have a nice day.